As we lift our eyes to the night sky, gazing into the boundless darkness of space, we are greeted by the mesmerizing twinkle of billions of stars. Each of these distant suns seems to pose a quiet, enduring question, one that has echoed through human consciousness for millennia. Are we alone in the universe? This question, profound in its simplicity, has inspired countless myths, scientific explorations, and philosophical debates. Today, thanks to incredible technological advancements, we stand on the threshold of possibly answering it. Leading this endeavor is a revolutionary instrument, the James Webb Space Telescope, JWST, launched into space by NASA in collaboration with the European Space Agency, ESA, and the Canadian Space Agency, CSA. The JWST represents a monumental leap forward in our ability to observe the cosmos. Its suite of cutting-edge instruments and its positioning far from Earth's atmosphere allow it to peer deeper into space and further back in time than any telescope before it. One of the JWST's most compelling recent missions involved turning its gaze toward a distant exoplanet known as K2-18B. Located approximately 120 light-years from Earth in the constellation Leo, K2-18b has become a focal point of scientific curiosity. This exoplanet is not just another distant world. It presents a unique combination of characteristics that make it one of the most promising candidates in the ongoing search for extraterrestrial life. Initial data captured by JWST revealed something extraordinary: the presence of water vapor in the planet's atmosphere. Water, as we know, is fundamental to life on Earth, and its detection on a planet outside our solar system is a tantalizing hint that similar conditions could exist elsewhere. But the discovery didn't stop there. Further analysis of K2-18b's atmospheric composition revealed additional molecules that deepened the intrigue. Among them was methane, a gas that, on Earth, is commonly produced by biological organisms. Methane is especially noteworthy because it breaks down relatively quickly under exposure to stellar radiation. For it to persist in an atmosphere, it must be continually replenished by some active process. The potential implications of this are significant. It suggests that there could be ongoing processes, possibly even biological ones, maintaining the presence of methane. Even more surprising was the tentative detection of dimethyl sulfide, DMS, a molecule that, on Earth, is known to be produced exclusively by living organisms, particularly marine plankton. DMS is not found in Earth's atmosphere through any non-biological processes, making it a strong potential biomarker. If its presence on K2-18b is confirmed, it would mark the first time a definitive biosignature has been detected beyond our own planet. This raises profound implications. Could there be microbial life in the deep oceans of this distant world, releasing DMS in ways similar to Earth's oceanic ecosystems? It's a possibility that scientists are now taking seriously. K2-18b's planetary classification further adds to its scientific appeal. It falls into a category known as sub-Neptunes, or super-Earths. These types of planets are larger than Earth but significantly smaller than gas giants like Neptune. Interestingly, our solar system does not contain any planets of this size, making it difficult to draw direct comparisons. The planet's mass and radius suggest it may have a solid core enveloped by a thick atmosphere, possibly consisting primarily of hydrogen and helium. Despite its exotic nature, K2-18b orbits within the so-called habitable zone of its star, a region where conditions could be just right for liquid water to exist. The star that K2-18b orbits is a red dwarf named K2-18. Red dwarfs are smaller and cooler than our Sun, which means their habitable zones are much closer to the star. In K2-18b's case, it orbits at a distance of only 0.18 astronomical units, AU, less than one-fifth the distance between the Earth and the Sun, and even closer than Mercury's orbit in our solar system. However, due to the star's lower Luminosity. This proximity does not result in extreme heat. Instead, it creates an environment that may allow for temperate conditions on the planet's surface. In fact, recent atmospheric modeling suggests that, with a stable hydrogen-rich atmosphere, K2-18b could maintain surface temperatures similar to those found on Earth, albeit with slightly warmer oceans. These findings have led some astronomers to propose a new class of planets that might be especially conducive to life, so-called Hycean worlds. The term, coined by astrophysicist Professor Niku Madhusudan and his team at the University of Cambridge, combines hydrogen and ocean, reflecting the key traits of these planets: vast, water-covered surfaces and thick, hydrogen-dominated atmospheres. In a groundbreaking 2021 paper, Madhusudan outlined the characteristics of these worlds, arguing that they could exist within a broader habitable zone than rocky planets like Earth. The thick hydrogen atmospheres of Hycean worlds trap heat efficiently, allowing liquid water to exist even at distances from their stars that would otherwise be too cold. Hycean planets could be up to 10 times the mass of Earth and twice its radius. Despite surface temperatures that may reach 200 degrees Celsius, their deep oceans, possibly extending hundreds of kilometers below the surface, might still support microbial life. These worlds may also be more common in the universe than Earth-like planets, and their larger size makes them easier to detect with current technology. All of these factors make Hycean planets, including K2-18b, prime candidates for future exploration in the search for alien life. Despite all this promise, studying these distant worlds remains extremely challenging. Even the James Webb Space Telescope must be used with extraordinary precision. Observing a planet like K2-18b requires astronomers to wait for a rare celestial alignment called a transit, during which the planet passes directly in front of its star from our perspective. During these transits, starlight filters through the planet's atmosphere before reaching JWST's instruments. By analyzing the changes in the light's spectrum, breaking it down into individual wavelengths, much like sunlight passing through a prism, scientists can detect the unique fingerprints of different molecules present in the atmosphere. This technique, known as transmission spectroscopy, allows researchers to identify specific elements and compounds that absorb certain wavelengths of light. If certain wavelengths are missing from the spectrum, it indicates that they were absorbed by molecules such as water vapor, carbon dioxide, methane, or possibly even dimethyl sulfide. These spectral signatures help build a detailed profile of the planet's atmospheric composition, which in turn informs models about its temperature, climate, and potential habitability. Ultimately, the story of K2-18b is still unfolding. While the current evidence is compelling, more observations and analysis will be needed to confirm the presence of biosignatures like DMS. Still, the discoveries made so far represent a monumental step forward. We are not only detecting distant worlds, we are beginning to study their atmospheres, climates, and chemical compositions in ways that would have been unimaginable just a decade ago. As technology continues to advance, and as missions like the James Webb Space Telescope yield more data, we may finally find definitive answers to the age-old question: are we alone?